record to the cloud. Okay, we start recording. Today is our first white paper deep dive. So it's going to be a presentation from Ayush. Take it away. Thank you so much.
Thank you, Gloria. Thank you very much as well. So I'm going to talk about speed security trade-offs in blockchain protocols. The paper was 15 pages, but it referenced another paper that was 40 pages. So I got a good amount of reading in this weekend and this week. So yeah, let's jump in. So yeah, this white paper deep dive hosted by Blockchain at Berkeley. Welcome. And just for questions, kept Gloria's slides in here. Feel free to just hit the chat box with questions. I'll keep it open so I can look at it. And I will pause at the end of every section for questions, just to keep pace and keep a pulse check going. So today, thinking about, first of all, just why even read this paper, then jumping into some background context, want to introduce the primitives associated with the model that these people used, and then kind of jump into high level, what is the paper arguing, and then just dive deep into it. So why read this paper? I thought this was a good paper to start out with because of how it tackles the proof of work concept, tackles Bitcoin. So I think there's three things. Just why it works and why it's so beautiful, especially proof of work consensus. I think this paper does a really good job of jumping into that and providing real solid mathematical arguments for why there is a high security tolerance for adversarial power in Bitcoin. And the second thing is looking at like immutability. So I didn't realize how non-trivial it is to make a system that is immutable, but also decentralized. Because in theory, a centralized system can be immutable if you just trust the person, but without that trust, then it actually is not a trivial task to make something immutable. But that was something I took for granted. The third thing is security. Let me open the chat. Yeah, so the third thing is security, and just what are the assumptions? First of all, what are the properties that make up a secure, robust public ledger? And what assumptions do you have to make in order to prove these bounds mathematically? Yeah, so let's get into it. First, some background context. Read questions out loud. Okay. Yes, I will read questions out loud. Thanks for that. So first, looking at the background, this paper that I read is, so this is not the paper that I read, but the paper that I read is basically an extension of this paper, which is a lot longer and tackles the Bitcoin, they call it the Bitcoin backbone protocol. They've basically broken down Bitcoin into a series of external functions and a series of algorithms that they use to model Bitcoin on a computer. So basically, they, from this, derived a bunch of security properties, proved decent bounds for security, for adversarial tolerance. And there's a couple things that, I mean, I think I just got from the first pages of this article. I did read the whole thing, but the double spending explanation that they provide here is really good because they use the bounds that they proved before. So as we kind of are familiar with, if a payee waits k blocks before receiving the services, then the probability that an attacker can reconstruct the chain drops exponentially by k. So that's like the validity argument of Byzantine agreement, which I will go over later. And this is kind of the point of blockchain, right? Like, it's immutable. Once you wait a certain amount of block confirmations, then it won't change, and you can believe that. The second thing is the way, which is the most important, is the way that they break down the quote unquote Bitcoin backbone. This paper was originally written in 2016, and it was revised on July 1st, 2019. So they call proof of work the Bitcoin backbone. Proof of work and the things built around proof of work like message broadcasting and things. So they basically describe the Bitcoin backbone protocol as a algorithm that is parameterized by 3 external functions that they define as validation, input, and reading functions. So these are abstractions that the miner actually puts down when they participate in the network. And based on tweaking these 3 things, you can actually create attacks and you can create applications that are good. So one of the applications that they claim is Byzantine agreement. So they don't think that the Bitcoin backbone protocol itself satisfies Byzantine agreement, but they propose a very simple tweak to the Bitcoin protocol, or rather a very simple application that can be built on top of the core protocol that establishes Byzantine agreement. And we'll kind of go over how they argue that. But for the purposes of my talk today, I think that this distinction is not very necessary to talk about, because as long as we prove that the core security features of Bitcoin are like valid, then it's a natural extension to consider how you can implement Byzantine agreement from that. So, and then, yeah, so then what is Byzantine agreement? It is basically these 2 properties as defined in the paper. So the first is agreement, which there is a round after which all honest parties will return the same output if queried by the environment being any user, for practical sake. As pace is the execution where they use tomorrow. And the second property is validity. So the output returned by an honest party P is the input of some party P star that P produces at the end of the same round. So that kind of says that the it's kind of the same thing as the immutability I was talking about earlier, that a transaction, if given to an honest party, will eventually appear in other honest parties' like ledgers. So we'll show how proof of work blockchains can support Byzantine agreement in the most basic way. Great, so that's the background of what the previous paper was about at a very high level. And now we can kind of go into what I am presenting about. Any questions on the other stuff so far? Cool. Oh. Yeah, I'll talk about the rounds soon. Yeah, okay. So let's start off with this. These are the 3 desired properties of a robust public transaction ledger in a black box. The first 2, common prefix and chain quality, come from the Bitcoin backbone paper. And the paper that I read introduces chain growth as as a third equally important property. So common prefix is, so these 3 properties are analogous to some of them are analogous to distributed systems. So common prefix is basically that all chains that honest miners are working on share a common prefix, especially if you cut off the most recent couple blocks. This is the main property that we're going to prove today because it's the most important for security, to prevent things like double spending attacks and to uphold immutability. The second property is chain quality. So miners that are honest do not have long strings of adversarial blocks in their chains. That kind of means that the chain was not subject to an attack. And specifically talking about long strings of adversarial blocks, because the way that an attack would form is by having an attacker mine their own adversarial chains. So there would be like an M long chain of adversarial blocks that would be appended to a good chain if it was attacked. So chain quality kind of is a proof that there, in this system, there would be no long chains of adversarial blocks, even if there are some in the shared honest chain. And finally, chain growth is important to satisfy liveness, because if the chain is not growing, then you cannot add things to it. So then it doesn't really uphold its initial intention, or yeah. So this property is proven in this paper. So now let's go over some key assumptions to prove these things. Any questions on those three properties? I think it's this paper specific thing, so it might not be the most intuitive.
How important is that? Like if you go back to the slide,
Yeah.
it talks about like you grow at like a bounded rate or a bounded coefficient. Is that like super important, or like where does that kind of come in?
Yeah, that is important because we'll talk about in a second the way the blocks appear. You don't want it to appear too fast. Like you want the block time to be consistent.
Oh, that's interesting.
Yeah. And there are natural bounds based on the protocol that you choose. So yeah, thanks for the question. So Gloria had initially asked a question about rounds, and now I'll explain that. So these are the key assumptions that the entire rest of the paper falls on, and the definitions that I'm going to use today when talking about speed security trade-offs. So a sentence here, we can assume that there's n total miners with t adversaries in a synchronous setting. So that means that out of the n miners, t of those are adversaries, and are full, everyone's connected to each other. Oh, I'm getting a message that my internet is unstable. Hello, and I'm back. So yeah, sorry about my internet. In a synchronous setting means that basically everyone's connected to each other. Yeah, so there's t adversaries and total miners. Everyone's connected to each other, can receive all messages. We basically take away all of the natural real world issues that would come with making a proof like this, like having different miners of different hashing power. What we do in this paper is assume that every n miner has an equal number of an equal queue, and that queue is the amount of queries they can make to a hash function. So it assumes a flat, oh, I had this written on the right. It assumes a flat model of hashing power. So that makes the proofs easier because you don't have to account for parties who have lots of hashing power. You just assume a flat model where everyone has the same power. And naturally, you can make an extension of this to capture a non-flat model by assuming that big players are simply groups of miners with the same hashing power. So if there's n total miners, maybe 5 of them you can consider as like one super miner, but at the end of the day, they have the equivalent power of 5 normal miners. And I'll go back to the left. So talking about a round, this is a very important primitive to talk about for this paper. A round, as it's defined here, is an instance of full network propagation. So every party, every miner receives a broadcast, receives a message, is able to spread out over the entire network. On average, this takes about 12 seconds for our proof of work blockchains according to the paper. So that is a round. And the way that we are going to talk about security and speed is through these rounds. And all the proofs will require the round as like the fundamental unit of time for these proofs. So a round is just, yeah, as I said, just one instance of full network propagation. And finally, the middle is F, which is the most important parameter. And F is defined as the probability of a successful proof of work calculation by an honest party during a given round. It's basically the number of blocks per round. And sorry, so it is defined as the ratio of propagation time to block time. So I think if that'll make more sense if I put it in context. So this is how we look at transaction speed. There's 2 main factors that govern transaction speed. One is the block size, because that affects how much data you have to, how many transactions you can put in each block. And the current 1 megabyte limit has been up for debate in Bitcoin. There's been proposals for 20x increases. But a key thing to note here is that when you scale the block size, the round duration scales by the same constant, because you have to propagate more data, so the round takes longer. So the actual TPS doesn't change too much. However, the second category is block time. So Bitcoin calibrates the hardness of its proof of work instances to maintain a block time of around 10 minutes. And that's to prevent the adversary from flooding the network with messages. So the TPS actually scales with F. If you look at the function at the bottom, or the proportion at the bottom, the transaction processing speed is proportional to the block size times F over the round duration. And if you remember that F is defined by the number of blocks per round, you essentially have block size times number of blocks means like volume of data. And then round duration, dividing by that would give you the volume of data per second. So that's transaction processing speed measured in like kilobytes per second. Any questions here? So no, so you would have, so Gloria asked, does round equal is get so you have multiple rounds per block, but the block time is 10 minutes and it takes around 12.6 seconds for one round to pass. So many rounds would go by potentially before a new block is mined. And that can be explained in the next slide pretty intuitively, if there's no other questions.
I'm trying to understand the round a little better. Could you go back to the round slide? Like
Sure.
these kind of messages. So like what kind of, yeah, like a broadcast, what kind of broadcasts are these? Like 12 seconds, like what exact kind of, I think kind of going off
So
like Simon's question. Yeah.
yeah, so to answer your question first,
Yeah.
it's just a message. So for example, like when you are a miner and you want to broadcast, like you mine a block, you want to
Yeah.
broadcast like that new block,
Mhm.
for every person in the actual Bitcoin network to get that message, it takes 12.6 seconds to achieve full network propagation. And for Gloria and Simon's question, 12.6 seconds, they pull from the Bitcoin network website, not the Bitcoin, or a website that tracks the statistics of the Bitcoin network. So this is just empirical. Yes, it does. And this stat is not a constant. It is an average of a lot of different, I guess, samples, because it does depend on engineering factors like, connection speed and network topography. The network is dynamic, which is one of the biggest assumptions that this paper makes, is that we're in a static setting with only n fixed miners. That doesn't change. So 12.6 seconds is just an average that they pulled from the network statistics, but yeah, it's not actually that important in terms of the proofs that we're going to get into. It's just to put things into context of how long a round is versus how long the block time is. Does that make sense?
Okay, yeah, that makes sense. I'm
Yeah.
also wondering, like, do they talk about like worst case as well? Like I'm a little confused about the synchronous word, because that sounds like synchrony. I associate that less with like connectivity, more of like, okay, like we're guaranteed that everyone has heard about this block at the end of the round. But I would think that in the worst case, it could be like a really long time. I don't know.
Even in like the normal case, you don't really have a guarantee that everyone in the
Mm-hmm.
network hears about a message.
Mm-hmm.
So that's definitely one of the shortcomings of this paper, but
Mm-hmm.
they assume that in order to be able to use math to prove the security bounds. So they assume that it's synchronous, and they assume that the number of parties is static. So those are the two main assumptions that it could involve more attacks that are not foreseen in this paper.
Okay, thanks.
Cool. So moving on, we covered this TPS, and yeah, so that makes sense. So this might put some of that into context as well. This is a comparison of Bitcoin to other cryptocurrencies in terms of their block generation rate and their F parameter. So Bitcoin has a block time of 10 minutes, 600 seconds. You can see other coins here like Ethereum, Litecoin, Dogecoin. And if you look at their F, Bitcoin has the smallest F because it has a hard proof of work. So, and the highest block time. So yeah, the number of blocks per round would be 0.021. And if you take the expected value of the number of rounds it takes to get a block, that is 1 over F. So it would take around 47.6 rounds on average if you use 12.6 seconds to get a block in Bitcoin. And you can see how that changes for other protocols. One thing to note is like, I was surprised that Ethereum had such a high I was surprised that Ethereum has such a high like F parameter. And yeah, looking at some of this, thought it was pretty surprising. So Gloria just asked, it seems like you would have block time, you should have block time less than round time. So
Or
yeah,
you
block time
shouldn't,
is,
yeah. Like you
yeah,
shouldn't be
that is
producing
correct.
blocks faster than everyone is able to catch up.
Oh, right, yeah. So yeah, the block
Yeah.
time being slow is a important security feature. So yeah, thanks for that. And the reason for that is because if people can catch up, then you can flood the network with messages, you can mine faster, and then people won't be able to catch up. So then you could get ahead of them and cause a fork or another attack, which we'll talk about. Cool. Yeah, are we done with the table? Move on. So what is the point of all that? The fundamental question we're asking here is, for a given block generation rate F, what is the maximum adversarial hashing power that we can provably tolerate by a population of honest miners? So while the assumptions that this paper makes are pretty strict in terms of deviating from what Bitcoin actually does in practice, this question can be answered if we make those assumptions. So let's basically just dive into what that'll look like. So the paper goes on to cover the model that they use. It talks about the Bitcoin backbone. It introduces chain growth, and it introduces an attack on Common Prefix. So I'm going to cover most of this. I'm not going to cover chain growth that in depth because I realize the Common Prefix proof is much more important for immutability. So let's get into it. All right, so a closer look at the parameter F. First, let's consider that obtaining a new block is achieved when you find a hash value that is smaller than the difficulty parameter D. And the probability of a single hashing query producing the solution is probability equals D over 2k, 2 to the k, where k is the length of the hash. 2 comes from binary hashing. That probability is proved in the appendix of the paper, which I did not include here. And they break down alpha and beta, where alpha is the hashing power of honest players. So that's n minus t. Q is the hashing power, p is the probability, and beta is pqt, which is just the adversaries. So F, which is the total hashing power, is just the sum of these two, like the total probability rule, and you get F. So F, in a more granular sense, is alpha plus beta. Oh yeah, and Simon Q, yeah, okay. Cool. And the reason Q is important is because every miner has a hashing power of Q, so it's a flat model. That's another assumption that we make. So any questions there before I talk about common prefix? Cool. So common prefix, I'm going to introduce this and chain quality at the same time. Common prefix is where two honest miners have the same view of the blockchain if they prune some blocks from the end of their chain. And the paper was a little bit confusing about start, end, and things like that. So basically, where the head, the last block is, if you prune from there backwards, going towards the genesis block, that's what pruning is. So if your blockchain has like 6 blocks, if you prune the last 3 blocks, then the first 3 blocks will be your prefix. So, which it makes sense, but just to clarify, prune is just like a hypothetical thing where you just like pretend it doesn't exist. And for the purpose of this proof, right? So basically, it says explicitly that if an honest party prunes K blocks, the probability that their pruned chain is not a prefix of another honest chain drops exponentially. So if you look at the diagram, the M1, miner 1 and miner 2 both have a chain that they're working on, and they have different blocks for the last 2 blocks, and M3. So they all have different blocks for the last blocks, then they share the common prefix X1, X2, and X3. So that is the common prefix that they all share. And the reason that this is an important property is because we want to prove that the probability of not having this common prefix is very small. Yeah, and I think a good phrasing that Gloria just put in the chat is like, the purpose here is to say that the blockchain K blocks from K blocks ago is definitely final, which is the biggest security feature that we're trying to prove today. So they go further to describe it as if the ratio of adversary to honest, which is T over N minus T, is suitably below 1, there is a large common prefix. Next property is chain quality. So this is what I was referring to earlier, where honest miners' chains do not contain long sequences of adversarial blocks. So the ratio of adversarial blocks, there's a typo here, but the ratio of adversarial blocks is bounded by T over N minus T, which is the same ratio of adversaries to honest people. And the ratio of adversarial to honest blocks is bounded by that. And they propose that there is a strategy for under favorable network conditions for the adversary that you can reach this bound. So those conditions would probably mean that the adversaries have like the strongest connection to the network, and they're like maybe geographically located in a way that gives them an advantage. But if they like rush and they keep on doing blocks, then they can reach this bound. So it is a tight bound. But this is not as important of we're going to kind of prove this today as well, but it's not the main focus of today. So Anamira asked, does suitably mean that they're going to parameterize the result bound with that adversary miner ratio? So so when I said suitably below 1, what I was saying is that I think it's more of a loose definition. It's just that there is a bound for T that is suitable. So if T is a suitable bound, then it wouldn't be able to be, the network would not be able to be attacked at T values below that bounded T. I don't know if that I explained it well, but that's what they mean by suitably, I think, is just like, is it below the bound that is proven? So this is a graph to take a little break. And if you look at the graph, you can see security bounds. So under the curve, if you look at, there's two curves. There's the GKL bound, which is the original paper that I brought up in the background and context section. And the green line is the new bound that is improved that we are going to prove today. So the proof for the old bound is included in the proof for the new bound. If you look at gamma U on the top left, so this is the GKL bound, the probability bound that a round is successful or uniquely successful. And these are terms that I will have to define eventually, but quickly, successful means that at least one honest party has mined a block, and uniquely successful means that exactly one honest party has mined a block. So this is the bounded probability that a round is either successful or uniquely successful. So the intersection of both those events, or rather the union of both those events. So we are going to improve that bound and remove dependency on F and simply create a new bound that is gamma is greater or equal to B. So I just want to check. I want to make sure I'm not missing questions. Okay, I actually just completely lost the bar, but it's fine. If you have questions, you should probably speak up at this point. So, yeah, Nish, you have a question?
Yeah, I'm a little confused on how to read this graph. Like the x-axis, like so.
Oh yeah.
Yeah, could you?
I'll go over it. Sure.
Yeah. Okay. Thank you.
So, yeah. So those are the two bounds. We're basically gonna prove the green bound. In terms of the graph, thanks for bringing it up. The area under the curve is the point where you would not suffer a common prefix attack. Or rather, the area under the curve is where the common prefix property holds. So the x-axis, which is the expected round, the expected rounds per block, is 1 over f. So for f being very large, you would have a small 1 over f, like Flashcoin is the smallest. Because their f is very large, they have a lot of blocks per round. And yeah, so the curve here is basically the bound that is proven by the paper to say that Ethereum can withstand 35%, for example, of adversarial hash power to have the common prefix property still hold. So Gloria asked, why is the hash power of adversaries need to make a CP attack? I think oh yes, and then the y the y-axis is, yes, the percent of hash power that the adversary has. So if there's 50% of the adversary, then like the common prefix property would not hold for either of these two chains. So this was a good graph. I like this, cleared things up for me as well. So yes, does that explain the graph?
Yeah, so like the new bound, that means that like, so that means that like we're actually more safe than we used to think?
Yeah, so this paper is saying that the bounds are actually better than what the original paper had proposed.
Okay, cool.
Yeah,
So
I
it's
think it's
like
really
we
cool.
can-
It's mhm.
Sorry, go ahead. So we can withstand a larger percentage of adversarial attacks among all the nodes, right?
Right. Then
Okay.
Yeah. And I think it's saying, even on top of that, as long as you don't make more than one block per round, there's no amount that the adversary could have to create a common prefix attack. Right? Because it's
Yeah,
0 until 1.
So I think it's not saying that there's no amount, but the area under the curve is the point where you are safe from a common prefix attack. So it's 0 until 1. I think that's saying that in the old
No, it's
bound,
undefined.
yeah, it's either undefined or it's just like saying that you're almost guaranteed to be weak. You have a weak common prefix.
Oh wait, no, I said that wrong. I think it's also what I think it's saying is you need to have at least 1 round per block. Otherwise, there's no guarantees.
Yes,
Right.
that's true. Cool. I'll move on. So now we're going to get into some proofs. Let these definitions hold for the rest of the presentation. So let's consider xi to be an indicator random variable for a successful round, as I defined being at least 1 honest player computing the solution at round I. So for those who might not be familiar with probability, an indicator random variable can only take the values 0 and 1, and x is the random variable in question, but x breaks down into multiple x sub i's. So for each round I, there is a corresponding random variable x sub I for that round, and x sub I equals 1 if the round was like successful for that event, or 0 if it wasn't. So x is the random variable that corresponds to at least 1 honest player being or mining a block, and it could be more than 1. There could be a tie. And y is a random variable for a uniquely successful round. So where exactly 1 honest player computes a solution in round I. And we're going to use these in the uniquely successful round is for security. So those 2 definitions are important. The third one is understanding an M uniform round. So there's the opposite of M uniform is just a uniform round. So a uniform round is where for all miners, the chains that they are mining are all of the same length. So it's uniform. But an M uniform round is that given any 2 chains amongst the miners, they have the difference in length of the chains that they are mining are in difference in length greater than or equal to M. It's actually less than or equal to M, but I wrote greater than. So that's a very, very important typo. So let's just clarify that. So if there's like 2 miners that have chains C1 and C2, these could be any combination of 2 chains from all of the miners, especially the honest miners, then the difference in length of C1 and C2 would be less than or equal to M. Okay. And then you can define base R as the shortest chain of all the miners at round R. So if we combine the previous 2 properties, we'll get the bottom, because you can consider at round base R, or rather at round R, if it is a uniquely successful round, then all miners will adopt base R plus Y sub R, and that will be the length of the chain that they mine in the next round, which is base R plus 1. If it is an M uniform round, then base R plus M will be less than or equal to the amount of blocks mined in the next round. So this inequality holds for basically all rounds, saying that the base R plus the max of either the random variable or random variable Y or M will be less than or equal to the shortest chain in the next round. So we're going to get into a proof now. First, we'll prove this lemma that says that an adversary must compensate for all uniquely successful rounds if they are trying to do an attack, specifically a 51% attack where they create their own longest chain. If they're trying to do that, then every time a uniquely successful round happens, they have to compensate for that round by mining their own independent block. And we'll use the previous definitions to prove this lemma first before proving the common prefix property. So this is the claim that we're trying to prove, that the lemma breaks down into, is that if R is a uniquely successful round that is M uniform, and there's some round S that is before R, then one, if the round is M uniform, then there exists a single chain C such that the blocks at positions base R plus 1 to base R plus M are all mined by the adversary. So the adversary has been mining all of these blocks. Yes, and that's an intuitive proof we'll get into next slide. And then the second part of that claim is that if it is a uniform round, M equals 0, then at the end of round R and onwards, for all pairs of honest party chains, if there was a divergence at round S, or any generic round before R, then there exists an adversarial block in one of the two chains at position base R plus 1. So we're basically just trying to prove that if there is a fork going on, then adversarial blocks are part of it. So let's prove this lemma. First, looking at the first case, that the round R is M uniform, that implies that a chain of length base R plus M must exist. Otherwise, it would not be M uniform. But at the start of round R, all honest miners have only mined chains at most of length base R. And the reason for that is because otherwise they wouldn't have chosen the shortest chain. So all honest parties and that implies that the claim that base R plus 1 to base R plus M are all mined by the adversary. And specifically, they're all mined by the adversary because the honest chains have not even seen this block yet, or this chain yet. And the second part of the claim is that if the round is uniform, then we can consider two chains that diverged at S. If they were both honest at base R plus 1, then there wouldn't even have been a fork in the first place. They would not have diverged, because if they're both honest, they would have been included in the honest chains. So that implies that one of the blocks on either chain must be adversarial at that position. So most importantly, taking these two claims together, plus the inequality that we observed earlier, implies that the adversary has broadcasted distinct blocks at specific locations on adversarial chains. So specifically, if you look at the random variable y, if we take a round, if we sum that random variable from around S to round R, you can get, let that be like a number t, for example. So t is the sum of all of the y sub I between around S and R. That's t. So what we've proven is that the adversary has mined t distinct blocks at t specific locations on t adversarial chains. So that's the only way that the miner is able to keep the forks going. So this is like a necessity. This is a necessary prereq for them to do an attack, and it's something that we can use to prove the common prefix property. This is a pretty long proof. This was like 2 pages, and I condensed it into 1 slide. So I'm sure there are some questions, but ask them if you want. It might not even be very productive to go deep into this, but I don't want to block any questions.
Yeah, I think this like slightly got lost on me a little bit, but I don't want to dive deep into it too much. So like, I don't know if you could just like reiterate like the point of this and like what this means. I think that's good. Yeah,
that's a good question. So it's basically the point of this, which we'll go into on the next slide, is that we're going to use this to prove the common prefix property. And this is important because if this property didn't hold, then we wouldn't be able to assume that the adversary is mining its own chain, And then we wouldn't have any kind of like base assumptions on what the adversary's chain is looking like. And then that'll become apparent when we prove the common prefix property. We should probably just get into it.
Yeah.
So let's look at this theorem 9. We're going to basically use this in a black box to prove the common prefix property along with the lemma from last slide. So as I said earlier, what we're trying to prove here is gamma is greater than equal to beta. That was the original bound that, not the original bound, but the new and improved bound that you saw on the graph, the green line on the previous graph. That is gamma greater than beta. So what this is saying is that assume gamma greater than beta by some constant delta, and let S be the set of chains that honest parties have at the beginning of a given round. Then the probability that S does not satisfy common prefix with parameter k is at most e to the minus omega delta cubed k. And parameter k is basically the number of blocks that you prune off the end. So this is pretty much what I had said earlier, and this is what Nakamoto had proven in the Bitcoin white paper and in subsequent like forum posts and things, is that the probability that there is no shared common prefix or no shared at a given round drops by k for every block that you prune exponentially. And so this relationship based on E is the relationship. And you can prove this using turn-off bound on the random variable y, looking at the previous slide, but that was a long as well included. And we can use this theorem 9 to basically prove the common prefix property. And the way we're going to do that is by showing that theorem 9 applies to only one round, but we're going to prove that theorem 9 applies to a given round and any round onwards from the given round. So if we prove that, we're essentially proving that a common prefix is shared indefinitely in the blockchain. So first, let's look at the definition of the common prefix property. And this is the strong common prefix property that the new and improved one that we're proving. So the strong common prefix property QCP with parameter k, as I said, k is the number of blocks that you prune, states that the chains C1 and C2 are reported by two honest parties, P1 and P2, at rounds R1, R2, where R1 is less than or equal to R2, are such that the pruned version of k, the pruned version of C1 by k blocks is a subset of C2, or that they share a common prefix. So yeah, any questions on the definition there? Cool, so the proof of this, by invoking theorem 9 a bunch of times, we can prove this. So if we go to the first case where R1 equals R2, that basically resolves to theorem 9, because theorem 9 says that in the same round, we can, for any set of honest chains, the probability that that any two of them don't share a prefix is e to the minus omega delta cubed k. So if we're talking in the same round, that basically is just theorem 9. So now moving on, assuming without a loss of generality that R2 is greater than R1, so that we're talking about different rounds, there's two cases. The first case is that party one, has a chain that extends C1. In that case, we're still talking about C1 and C2 in the same way that we were talking about it if the rounds were the same. Because if C1 extends, or if P1's chain extends C1 at R1, then at the point where you reach R2, you basically just have an extended version of C1. So you're essentially, which necessarily would have the same prefix. So you're essentially talking about two of the same C1 and C2 like you were before. So you can apply theorem 9 again off the bat. The second case is that P1 adopts another chain in between R1 and R2. So it suddenly stops working on C1 and it switches to C3. So this is a bit more complicated. If C3 does not share a common prefix with C2, then case 1 applies, because that means C1 and C2 are both in the same set as they were before. So theorem 9 applies there. There was no change to either of them, so we can apply it. However, if C3 does share a common prefix with C2, that implies that C1 doesn't share with C3 because C3 is bigger than C1. And that holds with the probability e to the minus omega delta cubed k from theorem 9. And because of that, we can say with overwhelming probability, because C3 is bigger than C1, and we can apply that to the theorem 9 bound, we have overwhelming probability that C1 does share a common prefix with C3, meaning that we can apply theorem 9 again because C3 and C1 have the same common prefix. So it's essentially like going back to the main definition. So basically, in all of these different cases, we've just reduced the scenario back to theorem 9, because we've shown that as long as we prove that there's an overwhelming probability that they're you're just comparing the same two generic chains, then you can apply a union bound and basically prove that the probability of no common prefix indefinitely is at most e to the minus omega delta cubed k. So this is basically the proof of the common prefix property.
Ayush, I have a question. How can case 2 happen?
Case 2?
Yeah, it seems pretty complicated, like that the scenario setup.
Yeah, so case 2 would happen if the party adopts another chain in between round 1 and round 2. So like in any way that party could adopt another chain than the one they had in the previous round, that's the way that case 2 would happen. So like if an honest miner were like mining their own chain, and then like there's like a new agreement on what the longest chain is, and the party like goes on that chain instead, like that's an example of what could cause this.
Sounds good.
Okay. Yes, and then the lemma comes in here because we cannot use this proof if we don't have the previous lemma, because this proof basically assumes that we don't have so if we don't have the previous lemma, then we can't assume that there is other adversary there. We can't assume that like the honest chains are honest, because we don't know what the state of the adversarial chains are. But now that we have the lemma, we know that the state of the adversarial chains are being mined in their own like continuous string, because that's the only way the attack would happen. So then we can prove this common prefix between the honest chains. Okay, but why did we even do that in the first place? The reason we went through all that math is because this means that Bitcoin and other proof of work chains are persistent. So if a transaction is deep enough in the blockchain, it will stay there, which is basically like the whole point of blockchain, in my opinion. So that's why I thought this was really important out of the three properties to like actually prove out. So you have this immutability as long as the common prefix property holds. So how much adversarial power can these proof of work chains tolerate before this property breaks? And if it breaks, then that's it. There's no reason to even use the blockchain if it breaks easily. So this is a beautiful graph. This is the same graph as last time with different coins that have larger expected rounds per block. So larger 1/f values. If you look at this is the number of hashing, the percentage of hashing power that the adversary could have. And under this curve is where you can have a common prefix property. So the common prefix property holds under the curve. Dogecoin and Litecoin are not that bad, apparently. And that's one of the keys of this paper, is that they were, with their new improved bound that we just proved, you're able to actually figure out that these altcoins are not that bad in terms of security. And Bitcoin is all the way here on the right. it's so much like more secure than the other ones that it doesn't even fit on this graph. So it's all the way here. Because Bitcoin has an expected rounds per block of 47.6. So this is not even proportional. That's like how far to the right Bitcoin is. So yeah, this is kind of just like the fruits of our labor of going through all that math is to approach this graph. And so yeah, so the final property of this paper is chain growth. This also has a 4-page proof, but I decided not to include it because it's more intuitive than common prefix, just like off the bat. So chain growth basically is equivalent to liveness in distributed systems, in my opinion. So for any chain, if you have the same chain, C, and the state of C at round S versus the state of C at round the current round, that's a difference of S rounds. All the chain growth property really says is that the chain will have grown by T times S, where T is a chain speed coefficient. And for Bitcoin, this chain speed coefficient is the same gamma that we just proved. So, or that we just used to prove theorem 9 and the common prefix property. Excuse me. So for example, in Bitcoin, that gamma is the rate of successful blocks. So the rate of successful blocks per round times the number of rounds is the expected number of blocks that would come after S rounds. So that's all the chain growth property is. And it's equally, this paper presents it as equally important to the two properties because common prefix and chain quality hold even if the chain stops moving forward. But that doesn't mean that you can't get Byzantine agreement unless you have a live blockchain. So chain growth is an equally important security feature for that reason. And they basically just prove that it'll grow. So finally, looking at the common prefix attack. So they came up with an attack that is basically just a 51, sorry, my throat's itching. They came up with a 51% attack that, yeah, it's basically just a 51% attack. And specifically on this graph, the area above the curve is a 1% chance of a fork that is 100 blocks deep taking over the honest chain. So yeah, they're just assuming that the adversary is rushing, that the hashing power is split between parties, and if the adversary can do multiple things like reschedule messages to keep parties split, and Ethereum randomly resolves ties, but they explicitly argue that randomly resolving ties won't work in this case because there's a 50% chance of the tie being in either the honest or adversarial party in the split. So basically this attack is bad, and this is the main attack that they're trying to prove security bounds against. So once they instantiated this attack, they ran the models on it, and they got, based on the bounds that we just proved, these following results, which is pretty cool. Ethereum has a tolerance of 35% for adversarial hashing power tolerance. Dogecoin and Litecoin are actually pretty good with 47%. Flashcoin is just like trash. They literally said in the paper that they can't even write a bound for it because it's just like unreasonable. And Bitcoin is the best as expected with 49% tolerance. So that was dope for me to read through. And more concretely, like, what is the speed security trade-off? I think this paper honestly got kind of lost in proving all the other stuff, that it didn't answer this question as explicitly as I wanted it to, but it does answer it, and the answer is that it's all about F, which is the number of blocks per round. If F goes to 0, like it does in Bitcoin, then your tolerance for adversarial hashing will approach the 50% bound. But if F goes to 1, meaning you have more blocks per round, then your tolerance will go towards 0. So F is the key parameter that scales TPS because it doesn't change the speed of a round, which is the speed of full network propagation. So the intuition is that longer block time with less blocks per round means more security in terms of tolerance for adversarial hashing power. So yeah, any questions? Otherwise, I'll just jump to conclusions.
Wait,
Yeah.
it should be if f is greater than 1, right? If
No, I think
f is greater than 1, then
so. F is yeah, I guess you could say that F is a ratio between the block time and round. So F is the number of blocks per round. So if F is greater than 1, then you're like kind of screwed. Which is interesting because Ethereum, I think, has an F greater than 1. It has like 1.05 or something. And yet they have 35% tolerance. So this is also a reason why the paper didn't explicitly outline any like truth like this, because it's more complicated. But this is like a general intuition that if you have less blocks per round, you have more, you can tolerate more adversarial activity.
yeah.
So yeah, I don't know if F, it's not like F would go to 1. I guess it would just be F would go away from 0.
Yeah. The higher f is, I think, the worse security. But that graph is really helpful. Like it goes exponential.
Yeah, it's pretty cool graph. Bitcoin master race. I think some things that are like were really cool about this paper is that with probability you can actually prove that we can trust proof of work. And there's like a reason for why. Like I think it was really cool for me to contextualize like why proof of work is so powerful. It is the original consensus mechanism after all. So yeah, it kind of turned me into a little bit of a Bitcoin, more towards a Bitcoin maxi. The second is that like public ledger, we have basically through the common prefix proof and a couple other proofs that I didn't include, you can basically prove that in a black box, proof of work works to create a public ledger that has a Byzantine agreement. So like without Bitcoin, without anything, like just like that kind of consensus works. And then that black box proof is really important because it would pave the way for future studies and just like more blockchains. And then finally, altcoins are not all bad in terms of security. So that it makes me less of a Bitcoin maxi, but Litecoin, Dogecoin, they actually have decent security. Ethereum has less security than I thought, but yeah, I guess like you can't just like not all altcoins are trash. Flashcoin is trash, but not all of them are. And the things that need research, in my opinion, are that, as we talked about in the beginning of the presentation, like this paper makes strong assumptions in terms of static number of parties and full network propagation in a synchronous environment. It doesn't really cover all the attacks. It only covers the 51% attack. So the paper even admits that the paper even admits that like this is not a full security analysis. There has to be more work done. And then finally, privacy was not really touched here. Security and privacy are kind of intermixed, but this paper was on a lower level protocol kind of side of things, whereas privacy kind of touches on the human side of things. So it would be interesting to see a work that relates like the privacy implications of having high or low security, things like that. But yeah, that's all I got. I would love to like discuss and talk about shit.
Thank you, Ayush.
Thank you, Ayush.
Thank you.
No problem.
I have one question though. I'm trying to
Yeah.
think about this in terms of like if you think about like scalability and like, so this is basically showing like how hard and why it's that hard. Like this what if you go to like that one side about like f about being between like 0 and 1, that like really showed me like, oh yeah, so this is really like, this is why it's really hard. You have to like keep yourself within this ratio while also scaling TPS. What do you think, like what do we do with like in terms of scaling if there's like this, if it's like this hard problem, like this really like, how do you think about it in terms of like these terms? What would we have to do
So
basically?
other people can feel free to jump in on this, but the way that what I'm convinced of after reading this paper is that the base layer you cannot scale too much on the base layer because you'll lose the security. So whatever we implement, like some layer 2 solution, probably the only way. Like I don't think you can touch the base layer.
Yeah, that makes sense.
Yeah, or like it's limited. Because base layer security and privacy, I feel like are the biggest priorities. But
Yeah,
like
you would have
even
to,
here, F strongly depends on network topography and latency, right? So like F is like round time and block time. Block time you can be pretty certain of, but round time might super fluctuate. And you can completely fuck it up if you manage to attack and partition the network, because then you could manage to prolong the round time by a really big, like really long. So
That's a good point. Like you
yeah.
could like take it if there's like a blackout, like a global blackout that like takes out half the world. You could like completely take advantage of that, so the round time would be like indefinitely increased.
Yeah. So I think I kind of disagree that they used the average block time or the average propagation time instead of like the worst case. But I guess worst case would be like you never actually reach everyone. So
I can actually here. I have the paper open. So I stopped sharing. Here, let me. Here, it's right here. Let me see if this makes that any clearer.
I posted a link as well.
Oh yeah, you can put
nice.
the link as well. Oops. Let me just control that. Yeah, so they say that assuming one full communication round takes 12.6 seconds, they say that this is the average block propagation time measured in paper 6, which is like an analysis on information propagation from 2013 though, from IEEE. Yeah, they pulled the stats though from some website like it's in a footer somewhere. It's like
I think a lot of miners are on this like somewhat shared note. Fuck, I can't remember what it's called. So that they can propagate to each other faster.
Interesting.
Can't remember what it's called.
It's like its own VPN.
Let's see if I can look for it. I was talking to Dave about it. Hold on. Dave. Fiber. Yeah, Bitcoin Fiber. Fast Internet Bitcoin Relay Engine is a protocol designed to relay blocks within a network of nodes with less delay.
Interesting.
Yeah.
Okay, look at this. This is horrible. The median time until a node receives a block is 6.5 seconds, but the mean is 12.6. So that means it's hella skewed right. So like it could get much worse than 12.6 easily. The long tail, even after 40 seconds, there are 5% of nodes that have not received the block.
Yeah. This is really cool though.
Like
it's like if we have these assumptions, we get these awesome properties.
Yeah.
Yeah. You need to have at least one round per block time though. That's what I learned today. at least one. Otherwise, you're fucked.
Yeah, I guess the average that they took is not unreasonable because the median is 6.5.
Mm-hmm.
So there's like some tolerance there.
Yeah, and maybe you don't need like every single node to get it, right?
Yeah.
So in some ways, kind of loose, in some ways, very strict.
Right.
I wonder if there's like a similar paper for this, but they use like proof of stake as the basis, and if they have like any analyses around that.
I was
Proof of
thinking
stake
about
is
that.
really different. I don't think
It's really hard to make
very
arguments around it.
different.
I don't know
But,
how you would even prove any bounds with it.
Yeah. But
Yeah.
generally, the bounds for proof of stake are like with Cosmos, because I had to like learn about this. It's like 33% stake, and then you also need to like partition the network a lot. So it's pretty hard. But yeah.
It's, I think, yeah.
Okay, Ayush, can you go to slide 32? Yeah, I think so. You mentioned Dogecoin has, well, or it's a Dash, not a Dash, Litecoin and Dogecoin has 47%. They can withstand 47% of adversary hash power. That seems like really good to me, and they're like their speed is much faster according to this graph that you show here, like right where you're at. So does the author suggest Dogecoin is a viable, or Litecoin is a viable replacement of Bitcoin? Viable altcoin?
Yeah. So I don't know. He doesn't. The author does explicitly say that Dogecoin and Litecoin are like a lot better than predicted, or like a lot better than the community like takes them for in terms of security. That was like one of his main findings. But like
It's also, I mean,
yeah,
so
right.
like Q, yeah, I feel like, so the equations, it's also cute, like in Bitcoin, for you to acquire more of the hash power is more expensive than for you to acquire more of the hash power in Dogecoin, if that makes sense. Like you also have to look at the total hash rate of the network, right?
That's actually a great point. So like even if percentage wise it can tolerate more adversarial power,
Yeah.
like it's easier to get that.
Yeah, so the graph is nice in terms of percentage, but you have to multiply that percentage by the current total hash rate of the network to get an accurate representation of what an adversary actually needs.
Gloria's gonna turn into a
Right.
Bitcoin maxi.
Wow.
No, I think it's like a lot of it is first mover advantage. Like
Mhm.
I remember I was talking about, oh, it was the first one, therefore, like, you know, it has a lot more. But like when we talk about theoretical guarantees on security of consensus, like this paper is really nice, but it was missing this part of like, okay, but like in actuality, how much is the hash rate compared to other altcoins? And like same with proof of stake, like I think theoretically it's been talked about a lot, but I think it's nowhere near being like actually tested in a real adversarial environment where the coins are worth like $8,000 and there's people actively trying to attack. Not to say that it never will be, but like Bitcoin does have that advantage that it's been tested over many, many years. Should I stop recording? I just realized if I'm talking out of my ass, this is gonna go on YouTube.
we can cut it out.
Okay.
Oh, yeah.
Thanks YouTube.